Good morning, everyone. Thank you, Professor Lee, for the introduction. Analog building blocks for DC-DC converters is one of my favorite topics, and if you ask a professor to talk about his favorite topics, it can take forever. So don't worry, we will still stay in time. So that brings me to the outline this morning. So we will talk about some motivation introduction first, and then we go into the building blocks which form the power stage, which is power transistors, gate drivers, and level shifters. And after that, we go into more classical analog design blocks which form the control loop of the DC-DC converters. And so then we put all together and form a control loop which brings us to some system level design aspects. So introduction. DC-DC converters are the major field in the growing topic of power management. There is a increasing variety of energy sources. So it ranges from a few millivolts of voltage we get from energy harvesting up to higher voltages into the range of 100 volts. So typical example are IT servers and automotive, where we get 48 volts as the input voltage. And now the task of DC-DC conversion is to convert these voltages to supply various ICs and functional blocks on ICs, which see the trend of a decreasing voltage towards 1 volts approximately. Right? For power reasons, simply for power efficiency reasons, we go further down. So we need to bridge this with DC-DC converters, and there are a couple of key care abouts. First of all, we want to be power efficient, but at the same time we want to be compact, so small size, small volume and footprint is essential. Then there are more aspects like we want to be immune against noise incoupling, EMC, these topics come into play. And finally, it shouldn't cost much. So of course we need to be cost aware. Power management systems can be either part of functional ICs to supply the various blocks, or there is a growing class of power management ICs which are purely dedicated to power management. So I've displayed here some examples. The first one here is on portable devices which run for relatively low voltage batteries, for example from a lithium-ion battery, and there are subsequent DC-DC converters and voltage regulators. So these buck converters are actually the DC-DC converters we talk about. And then we get the various voltage levels that supply our different electronic blocks. The situation is almost similar if you go to higher voltages. For example, in cars, we see quite large voltage at the battery level, and then we down convert again to supply various blocks. The difference between the more portable solutions and automotive or IT service is that we have a higher conversion ratio in the latter case. So that has some impact on the control implementation and of course on the voltage capabilities of the involved building blocks. The key fundamental concept to do DC-DC conversion is pulse width modulation. So I would like to outline the scenario here on the left-hand side by this picture. So we use a power stage which consists in this example of 2 transistors forming a half bridge. We look into that in a few seconds. And then we hook up to passive components, L and C. And what we get is here, we by turning on the switches, alternating the switches here, we get a pulsing waveform over time. So it ranges from 0 to the full input level. And then this is brought onto this LC configuration, which has 2 functions. The first one is energy storing. So if the switches are disconnected from the energy source, we want to keep the current running, so the output current can be still delivered. This is ensured by the inductor. And the second function is filtering. This LC forms an LC low-pass filter and basically generates the average of the switching node voltage. And that brings us the output voltage. as seen here on the right-hand side. So by changing the pulse width, we can adjust the output voltage. This is the fundamental principle. So if you look at a real-world example, it looks as seen here on this photograph on the left, lower left. So we have the IC, which is quite compact and small, but there is still a relatively large space required for the passive components. So state-of-the-art switching frequency is roughly 1 megahertz. And now the idea to bring these components down is to simply decrease the storing time, which means we switch at a faster frequency. And as we can see here, the higher the frequency gets, the smaller our components get. And we get eventually the chance to go for a package level co-integration of these passives, or even can integrate those passives on chip. So let's look into the control loop. Now we add a controller, and then we can put together the full DC-DC converter. So in between the input and the output voltage, we have the power stage. And then we add basically a so-called error amplifier, which has a certain frequency behavior. So, and that's why it's also referred to as a compensator. And that's brought into the pulse width modulation, which we will look into in a few minutes. So that altogether has to be stable under all conditions, of course. And we see already a lot of building blocks which are of interest and which will be addressed during this talk. So it's the power stage, switch, gate drivers, level shifters, and then in the control loop, error amplifier and various other components, including protection and also current sensing. The design of these blocks is closely related to the technology options. So we've got a variety of low voltage and high voltage transistors, in addition to various isolation capabilities, buried layer isolation, trench isolation. And on top of that, various components like Zener diodes and Schottky diodes. And there's also non-volatile memory available. So, and that helps us to implement these DC-DC converters for various applications. So let's start with the first part. The key part is the power transistor itself, the power switches. They can be in the switch mode DC-DC converters. They can be found in 4 typical configurations as shown on this slide. So the first one on the left is the low side. So the transistor is placed at the low side with the load then connected up to battery. The opposite is the high side. And if you put both together, we form a half bridge. This is what we have seen a few slides back at the earlier example. And if you use 2 half bridges, we can form a so-called full bridge, and that looks like the character H, and so it's sometimes also called H bridge. Depending on the power level, transistors can be either on-chip, fully integrated, or we use discrete external transistors if the power levels are higher. In general, as long as the voltage ratings are fulfilled, any transistor can be a power switch. For high voltage and high power applications, usually N-type transistors are preferred, as shown here in these examples, because we get simply a lower radius on and lower area for an N-type device. So if there is higher power, then we want to place an external power transistor. There are various types available for different voltage classes, different on resistances, different switching behavior, and so on. But it's really interesting to integrate those transistors on chip if the power levels are not too high. So what can we achieve? Typical on-chip on resistances are in the range below 1 ohm, so 100 milliohms is easy to achieve. Takes some space, some layout area, but it's doable. And we can carry currents in a few amps range across the die. And that all comes together with voltage capabilities up to 100 volts typically. So that's quite interesting. That's why we put the emphasis on integrated power stages in the next few minutes. But let's first review a little bit the switching behavior of transistors. So on the left here, I have the transient, the most important transient waveforms for the turn-on phase. It will be similar, quite similar for the turn-off. That's why I've left it out. And we assume switching of an inductive load. We have some inductors tied to the DC-DC converter as part of the DC-DC converters, so we have inductive switching. And then we basically see four phases. So the upper graph is the gate source voltage. So we ramp up the gate voltage and then further to the final maximum or the final targeted gate source voltage for a targeted on resistance. So what we see here in the center, this Miller plateau, is actually one interesting effect, which is similar to what we probably have all learned in the analog amplifier theory, the Miller effect. So during this phase, we see a steep transition of the VDS voltage, if you turn on, right? And during that transition, almost all current goes into the gate drain capacitance. So we charge the gate drain capacitance, and there is almost no current charging the VGS. And that's why the gate source voltage stays almost constant. And that's why we see a Miller plateau during that phase. Once this is done, we ramp up to the final VGS value. So if we now take the VDS and the ID transients and multiply them, we get the instantaneous power dissipation, and that allows us to identify that there is a dynamic power dissipation during the transition, and there is a static power dissipation, which can be all calculated, and I've given a few example values, which indicate that these values are in the range of a few hundred millivolts. So it's considerable, the power dissipation, and one of the goals is usually to optimize to get to a lower, the minimum power losses. There's on top of that, since we are charging basically the gate capacitor, it's gate drive losses which come on top of that. And especially since they scale with frequency, especially frequencies go higher, they also contribute significantly to the power losses. If we have some higher voltages, the preferred component for the power switch is the double diffuse MOS transistor, the DMOS transistor, which comes in two flavors. One is a vertical version, and the other one is shown here. That's the lateral DMOS transistor. Lateral means we can place them on a die together with all analog and digital circuitry together. So that allows really a fully integrated DC-DC converter. So how does this transistor look like? First of all, here, this is the source in the center. There's the gate, left and right. It's a symmetrical device. If you look from the top, it's like a circle shape, and the drain is the outside area here. And now we can observe three characteristics. The first one is, due to this symmetrical shape, there is quite a large cross section, and that means we have a low on resistance. That's what we want to achieve here. The other point is, there's some noise. Is that here or coming? Hopefully it works. No. So the second point is the drain is in a distance to the center part, and that's the so-called drift region, which gives us the voltage capability. So we get low oddies on high voltage. And the third point is, if there is one transistor of this shape not giving us a sufficiently low on resistance, we place multiple of these fingers in parallel as outlined here on the right hand side. So we can really take the drain of one transistor and overlap it with another cell and so on, and we can place a few hundred of those in parallel, and that's what is done in reality. With that we get quite a nice power transistor which has also high voltage capabilities, in some cases up to 100 volts. We also notice that there is some junctions, 2 junctions actually, which are typical. This is the first one, a PN junction, which is the so-called body diode. And the other one is the substrate diode. So if we add this to the transistor symbol, they are always there as shown here. And they do not always have a negative effect. They are sometimes even quite usable, for instance, as a freewheeling diode if you do inductive switching. They also form a nice power diode, by the way, so this can be used. The body diode is always present, even for regular transistors, standard CMOS transistors. We would also have the body diode as indicated here on this slide. So if you form a half bridge of 2 N devices or P and N, there's always the body diode as indicated here. And this is important because sometimes our let's say the output voltage exceeds the battery. Sorry. The battery supply voltage, and we may get some kind of back supply through the body diode. So that's something that we need to be aware of. And the main issue that also can cause, as here the second item, if the body diode goes into forward conduction, we see losses basically, because we have the forward voltage times the current, that's additional losses. So we want to avoid that as well. But the major point is that there is not always only a PN junction, there is always a bipolar transistor associated with it, a parasitic bipolar transistor, which I'm indicating here for the case of the DMOS transistor again. So that's a part of the cross-section of the DMOS device. And now remember, we have inductive switching, so it may happen that our drain connection gets pulled below ground, and then our substrate diode forms a base emitter junction of a parasitic bipolar transistor. And any other N area which is nearby, that forms the collector. And so you see already what's happening. There is some current pulled out of that N area here, and if this is a sensitive circuit, we may get at least some disturbance. It may even cause some debiasing, substrate debiasing, or in the extreme case, this may even lead to latch up. So we really want to avoid it, and one of the common concepts to avoid it is to place a guard ring, shown here at the bottom. So basically, the guard ring is inserting, can be formed if we insert an N area here, and then this takes over the role of the collector. So if you will, it's an artificial collector, and so nearly no current is sucked out of the sensitive circuit anymore. The drawback, we see that already, is that this takes some area, and I know from my experience, usually that's not in the, if you do a die size estimation for power transistors, this is usually not really planned for, and that's why I'm highlighting. It takes area, layout area. There are some applications which even place multiple guard rings, 2 guard rings or triple guard rings, and then it takes quite some additional area around the power transistor. To even get the sensitive circuits more protected, we can use isolation by inserting some highly doped N areas and encapsulating the sensitive analog blocks, so that gives an additional protection. And I do this for many years, these concepts, so guard ring, of course, plus isolation, and we had never any issues with coupling, which otherwise, due to the bipolars, is still quite a risk. There's one more issue I want to briefly outline. The isolation is usually done by reverse biased junctions. So we have some isolation area as indicated here. So that's encapsulating our power stage, and if that is hooked up to the switching node, which is a common practice to have that, then we see this the potential moving up and down at a very high speed, and with fast transitions in the few volts per nanosecond range, and that causes displacement currents, which again cause substrate debiasing and may even cause bit flips in digital circuits. So what you want to do is you want to take away this current immediately at the source where it occurs, and one of the most efficient measures is backside metallization. So if you have some metal which is grounded at the backside of the die, you can suck the current away without getting too much disturbance. Just want to briefly outline this. This is another big topic here in the field of DC-DC implementation. One more topic, these switches can be quite large. So in the end, that represents a large gate capacitance which needs to be charged and discharged to turn on and off the device. We have also learned that we go to higher switching frequencies in the few tens of megahertz, and so these capacitive charging and discharging losses, they get significant. And it turns out that it's much more efficient to use a stack of low voltage transistors instead of high voltage devices because of that reason. So as these low voltage devices have much lower parasitic capacitance. That can be nicely seen here also in this plot, which shows the on resistance at the x-axis and relates the losses, the energy loss, which includes the DC losses, the static losses, and transient losses. So, and there's always a minimum. And these three curves indicate now the 5-volt devices, PMOS, NMOS, as well as two stacked NMOS devices which are rated for 1.5 volts. So, and this is a log scale, and it already indicates that there's a significant reduced losses if you use these stacked transistors. And you could do that also for area, in terms of area, layout area. Also here, the stacked version WINS has significantly lower area consumption. So it's a benefit. Of course, it's more complex, but anyway, it has a lot of advantages, so it's highly recommended to look into that if you have fast switching applications. That brings me to some more useful configurations with power switches, which I want to summarize here on this slide. So on the left, we see a so-called back-to-back configuration. So the standard case is that we have an input voltage and we somehow bring that voltage down to a lower voltage V2. But this is not always the case. If the V2 exceeds V1, then even if we turn off our transistor in the regular, if we have just one switch, we would get some back supply across the body diode. Yeah, we turn off the transistor, channel is cut off, but still the body diode is always there, and that would get conducting if V2 exceeds V1. And if this is something we need to address, then the only solution is to place two devices back to back, as shown here. So the diodes can never conduct. If we then turn off the switch, there is no channel anymore and no conduction, so we prevent this topic of back supply. And the only drawback is if we have two transistors, we basically double the length of the device, and if we want to keep the same on resistance, we need to also double the width, which brings us 4 times the area. So we only want to do it if it's really necessary, right? Let's look into the center here. This is an interesting circuit which uses a high voltage transistor in a cascode configuration to protect a low voltage device. And what is the use case? Sometimes you want to benefit from the really superior analog capabilities of low voltage devices in a high voltage environment. One example could be the error amplifier in the control loop. So we have seen that already. You sense the output voltage. You want to do that precisely. In the error amplifier, our differential stage would be still a low voltage transistor with nice matching capabilities and so on. But it may, this transistor may see some high voltage at the gate, and that's why it's very convenient to place this high voltage transistor as a protecting device here. There's one xenodiode here as a secondary protection that clamps basically the gate source voltage on top of the protection by the high voltage device. And all we need is now a bias voltage here at the high voltage transistor. And if you have any low voltage supply rails, like a 3-volt digital or analog supply, you can hook it simply up to that rail, which comes almost for free, and then you get this protection capability. Another nice application is power sequencing. If you have multiple DC-DC converters, you want to have the enable pin of the subsequent DC-DC converter and hook that up to the previous stage, and once the voltage is up, you want to turn on the next one. And that can be also done by a low voltage transistor as a sensing element, which needs to be protected by a high voltage device. So that brings me to the last configuration, sometimes called active zener. It combines the precise clamping voltage generated by a xenodiode in addition to a power device which brings you the current capability. So that's a high power voltage clamp for protection purposes, for instance. And in the same way, I want to go to the next slide, we can implement what is called shunt regulator. So it also uses a xenodiode which is biased, and then we hook it up to the gate of a power transistor, and that can deliver now quite a large current out of a whatever supply. We get a voltage of VZ minus VGS, and if you don't want to have the VGS here in the equation, we can add one more transistor here in the diode configuration, so that compensates the VGS, and you get roughly VZ as the output voltage. So what is it useful for? It can deliver you a coarse supply for let's say a non-critical digital block, or we can use that as a pre-regulator, in some cases even as a standby voltage regulator. It's a very simple circuit. It's, if you will, it's open loop. That's why it's very fast. But of course, it is not very precise since it has no real control loop built around. So that brings me to the interim Q&A, which has been a good practice over the last couple of years at these tutorials at Isscc. So if you have general questions which may help you and also others to understand and follow this tutorial, feel free to ask these questions. Okay, thanks. Then I'll probably continue. So that brings us to the topic of gate drivers. Gate drivers is very simple. It's a very simple circuit. It just needs to turn on and off the power device. So very simple, but if you look in detail, it's still a little bit more complex. So on this slide we see there is, of course, the power transistors. Just as an example, I'm using here a high side transistor. This is the low side transistor. That includes also protection. Protection could be over temperature, protection against over voltage and over current. And then the main block is the actual low side driver, high side driver. That ensures that we provide the right gate source voltage to turn on the device with the targeted gate source, with the targeted on resistance. And since the control voltage here can be relatively low, if it comes from a digital controller, we can run this with 1.8 volts, for instance, while the gate source voltage will typically be at 5 volts. So we need to have some kind of level shifter in between for the high side as well as for the low side. And then our actual gate drive voltage comes from a so-called gate supply. In many cases, we use a linear regulator to provide this voltage, for instance 5 volts. And in particular for the high side, we sometimes need an additional supply which is using the principle of bootstrapping, which will also come up in a few minutes. And the last block is dead time control. So for the bridge configuration, if we connect this high side and low side device to form a bridge or half bridge, then we always want to make sure that there is no cross current. Otherwise, usually we would damage the power stage. So, and that's why we need to have a dead time control, which it first turns on one device before the other one turns on. Turn off before the other one turns on. Right. Okay. Let's look into the general principle of gate driving. So on the left, I have the low side driver as an example. So our power stage, here at the low side, the transistor, the load hooked up to the input voltage. And then we have the driver, which basically either connects the gate to ground or pulls it up to the correct drive voltage level. So that's the first task of the driver. We provide the sufficient gate overdrive. The second requirement is that we want to drive fast. So if you ask your system engineer or customers, you want to drive fast, they always say, yes, I want to drive as fast as possible. And that also relates to the question that just came, how do we optimize the efficiency, the transition losses? We want to get the transition and switching losses to a minimum value. So we want to drive very fast. Of course, there's always some parasitics, some characteristics involved, which I'm showing here on the right. So let's summarize these points. First one, of course, is the targeted gate drive voltage we drive. Typical values are in the range of 5 volts, sometimes a little bit higher, sometimes 8 volts. The next point is the gate driver. It has a finite resistance. Of course, these switches are not 0 ohms. So they have a finite resistance of typically 1 ohm. And that corresponds to a current, which actually we are driving the gate. That means we have just a capacitive load. And so our current will be a peak current, and that's in the range of 1 amp. So quite a large current for a short moment of time that needs to be delivered by the driver. And especially if we have external power stages, then our transistor can be a little bit in the distance from the driver, and this connection, this gate line, will be a parasitic inductance at the same time. And that's usually also to be optimized to a minimum, otherwise it degrades our speed. And it may even lead to some DVDT trigger turn on, so the transistor sees some peaking, shortly turn on, always failure cases. And in extreme cases, we may even exceed the maximum gate source voltage and damage our power device. So this gate inductance, just want to briefly mention that, that's a big topic for larger power, DC-DC power modules. So let's look into a real circuit, how such a driver can be implemented. And that's really an example of a real-world driver. So there's almost all components included. It shows these 3 major blocks. On the right, we see our power transistor. And then we control it at the left here from some control logic, which can run from a lower voltage, let's assume 1.8 volts or even 3 volts. And then we need to send this voltage to a level shifter, which is then operating from the V-drive voltage. So this is an example of a fundamental level shifter, so-called cross-coupled level shifter. It has 2 complementary outputs. So let's assume we turn the input signal here to 1. That turns on the N device here and pulls down the V out N voltage. In turn, we turn on the other side here this PMOS, and we pull up V out P. So we have complementary outputs, and we just use the V out N, which is in our example pulled to ground, to 0. And so this is brought to the actual driver, which is formed by an odd number of inverters, CMOS inverters. So if we have a 0 at the input, we get a 1 at the output, and we turn on the low side transistor. So for small power transistors, it would be sufficient to use just 1 inverter. If the transistor is larger and we want to drive it fast, then we want to use multiple stages. This is the same theory that is known from the 1970s for driving off-chip loads. And since this plays a plays a major role here. I would like to highlight that a little bit more in detail here on the next slides. But first, let's look at an example. This dye photograph shows a dual step-down controller. That means it's a controller, means there is an external power stage used, so external discrete power transistors plus the LC low-pass filter. And since we want to drive quite large power transistors, we use multiple driver stages. And each stage increases in driving strength by a factor of alpha. And in the end, we want to drive quite a large power transistor, which accounts to a gate capacitance of 10 nanofarads. And if you want to drive that within 15 nanoseconds, we really need to have a large driver. And we see that here the N-type device in the last driver stage has a width of 1.3 inch, so 3.2 centimeters. So it's really, really large. And that's not the power stage, it's just the driver. That's why it takes quite some layout area. So each high side and low side together is roughly 1 square millimeter. And why is that? Because we want to get a driver resistance as low as 3 ohms, which corresponds to a driver peak current of 1.5 amps. So that already indicates it's worth to spend a little bit of time to optimize the design and the sizing of the drivers. And that is related to the question, how many stages do we need? A number of stages N. And what's the scaling factor alpha, sometimes called tapering factor? So let me summarize the general approach. So there is different design goals for these drivers. So in the majority of cases, we want to have a minimum switching delay. So this is one design goal. In some cases, in low power designs, we want to have the minimum losses, means the minimum power consumption for this driver. So it's a different goal, and that correlates a little bit to the area consumption, so the layout area that we need to spend to implement these drivers. So, but in general, there's always, we always want to make sure that we do not get a DVDD trigger turn on just through the drain gate capacitance. So if that is the case, and that can be verified by simulations, if that is the case, we simply need to decrease our drive resistance by increasing the WOL of the last driver stage. So let me quickly summarize the approach, or the sizing approach, in terms of number of stages and scaling factor. So this is identical to what was investigated in the 1970s for driving off-chip loads. So we start with a simple CMOS inverter, and we have one of these inverters at the load as a load of the inverter itself. And we can define an average propagation delay for such a stage, which basically accounts for an RC delay that we see here. And now if we replace the inverter by a real power-fed power transistor here as the load, we get a large load capacitance that needs to be driven by this poor little inverter. And so what we get is, I call that direct conversion time, or it's again RC, and we substitute the R by the equation we found here. And then we see that we scale the average propagation delay by the ratio of CL over CG. So CL is the capacitance, or the gate capacitance of the power transistor, which is really large, and CG is the input capacitance of a minimum sized inverter. So there is, of course, quite a large time required. And now we go into an optimization. By adding multiple stages, which are all increasing in driving strength by a factor of alpha. So if we look into one section here, we see that the output load capacitance is always alpha times larger than the input capacitance. And that's why we can put together this equation. And I need to apologize, there was one equal sign missing in your printout. So if you want to add this in your notes, then you have the right equation. So if we have a scaling of alpha, we can insert what we learned about the direct scaling here, and then we get basically alpha times APD, TAPD as the delay of one stage. And if you have n stages, this is the equation that defines the delay of one of these configurations with cascaded inverters. So now we want to optimize it, so we put together the ratio between T cascade to T direct, which is a expression that consists of two terms. The first one is given by the application. It's simply the ratio of CL over CG. We can't do much about it. The second term, this allows us to optimize, and if we plot this term here as a function of alpha, we get a minimum which is exactly reached at Euler's number, which is 2.7 roughly, right? And so with that, of course, this is just a simplified model. In reality, we get alpha values between 3 and 6. And from that, we can calculate the number of stages. I've added some examples. I mean, this is always good to have some feeling based on examples. If our power transistor has a gate capacitance of 300 picofarads and our inverter has CG 30 femtofarads with an average propagation delay of 1 nanosecond, we can we see already that the direct driving of this little inverter drives this large power transistor. It takes us 10 microseconds. That's really long. It's actually not acceptable. So if we go then to a cascaded approach, with the alpha set equal to Euler's number, we need 9 stages, which gives us 25 nanoseconds. So here we are. This is a value that's acceptable for gate driving. If we modify a little bit and say, okay, we go to a larger alpha, we set it to 6.3, then our number of stages reduces to 5, and that's actually still not increasing the delay so much. It's 32 nanoseconds, so it's in the ballpark. So it allows us also to make our life a little bit easier by using a lower number of stages. This is the optimization for speed. If you want to optimize for power, just to outline this briefly, we need to imagine the more stages we have, the higher the number of stages, we have more inverters that have a cross current. So, and that all adds together and causes excessive losses. I'm showing this here in this graph. So the switching losses, depending on the number of stages. So the more stages we have, this dashed line goes up, which are the driver losses. So more number of stages, more cross current. If we have too few stages, then we do not have the right driving capability, and our loss triangle for the switching losses increases. So again, our losses go up. And there's an optimum somewhere in the center, in this example for 5 stages, which also was investigated in a couple of papers. I'm just highlighting 2 quite useful papers in that field if you want to look it up later on. The bottom line is quite simple. We don't want to use too many stages. So if you want to really get your power consumption for the driver to a minimum, don't use too many stages and rather increase the alpha. So that's the rule of thumb I'm summarizing here. There's one more detail. We have learned that the last driver stage can be quite large. And so we can imagine that the cross current at that final stage is significant, and in fact it can account to 50% of the driver losses. So we really want to do something about it. And this is the scenario. So if we have some inverters here with also some example values of W over L added here, what we can do is we split our, we keep the final driver stage unchanged, but we split the previous stages into 2 branches. So one branch to drive the pull-up device of the driver and the other one for the pull-down device. Since we simply use the same transistor size, we just split it into 2 parts. I try to indicate that here by colors, right? We have yellow and red and green and blue, and that goes in 2 parts. There's almost no area penalty except for additional wiring overhead, but there's no area penalty, so it comes almost for free. And now if we have two separate branches, we can drive the power stage and the last final stage separately. And there are two interesting methods to do so, which we can look at now on this slide. There is the very common principle of a break before make circuit. What do? We simply sense the turn off of one device, of one of the final power pull down device in this example here, and then we feed that back to the turn off path of the other one. That works quite nicely, except that the signal propagates 2 times through the driver chain here. And likewise in the other case here, vice versa. And that's why the process variations and all tolerances have some impact here, and in the end you will always need to do some over design, add some design margin, and that's the drawback. So for general purpose it works. In particular, if you want to go for faster switching DC-DC converters, the concept of asymmetrical driver sizing is much more effective. It's basically an open loop concept. So here we see there is some feedback, that's a closed loop. But here we have our open loop. All we need to do is we start from a driver design that we have optimized for speed or for power, as we have just seen a few seconds ago. And then we increase and decrease the driver strengths, make it weak and strong, so that we always have a strong turn off and a weak turn on. And with that, we get always some delay in between turn off and turn on, and that's our dead time that we add here to reduce the cross-conduction effect. So, and the typical weak-strong sizing is in the range, I call it asymmetry factor, is in the range of 20 to 30%. So we offset our nominal value by that percentage, and everything works. Let's get back to our high-side device. So the high-side switch, there are actually two types. The most common type is shown here. So we have the gate driver with its ground connected to the switching node. And this is to make sure that we do not exceed the maximum ratings for the gate source voltage of the power transistor. If we have just a low voltage DC-DC converter, we can also use this concept here and refer the driver to ground, but it's sometimes not possible to do so. Especially if we have a N-type device here, we want to make sure that we provide the proper gate overdrive. If you imagine the device turns on, then our switching node will approach battery voltage potential here. And we need to provide a voltage at the gate that is higher than the battery level to keep the transistor turned on. And there are various ways to supply that voltage. In particular, for DC-DC converters, the bootstrapping concept of bootstrapping is very well suitable. In addition, of course, we can use charge pumps and we can use boost converters for a proper gate supply. Again, an example for a high-side driver, also a real-world example. We can implement it right away. There's nothing hidden, and that would work. So we have, again, the power stage here, the high-side transistor with the control here on the left. And it's quite similar to the low-side driver we have seen already, except that our level shifter is a little bit different now. That's actually the most simple thing you can do to level shift. We have just a switch and a resistor, and everything is hooked up to the supply rail for the high-side transistor. So the driver can be, again, formed by multiple stages of inverters, and key careabouts are the resistor value. If the resistor is too low resistive, of course we have fast switching then, but we load the V-high supply a lot, and we want to optimize that. And typical values of this resistor are 100 kilo ohms, then everything is fine. The second point to consider is we want to make sure that the voltage here at the gate doesn't go too much down so that we exceed the max ratings of the gate source voltage here at the driver input, and that can be ensured by these clamping diodes, either a Xeno diode here or also very, very nice this diode here between the ground and the switching node and the drain of this transistor. So the bootstrap supply. This is the gate supply for the high side device. Let me outline the principles. So we make use of the switching nature of the bridge, and if we have our switching node at ground level, we simply charge a capacitor, the bootstrap capacitor, through a diode from a VDD voltage, which could be 5 volts, for instance. So we end up at 4.3 volts roughly, and we charge the capacitor. And now all we want to do, or all we need to do, is we connect the top plate of the capacitor to the high side driver supply. And once we turn on the high side, our switching node approaches the battery level, and the diode here gets reversed in reverse or blocking, so that our sole energy supply is the bootstrap capacitor. And that needs to be sized properly so that it delivers all the power that is required. And that mainly is the gate charge. In addition, we have some reverse recovery losses of that diode. We have leakage currents, and there's also some DC currents which we need to deliver at the high side to the level shifter and so on. So there are some example values here, and if you do the calculation, we end up in a range of 100 nanofarads. So 100 nanofarads is a typical value. If you look at data sheets of DC-DC converters, usually you place 100 nanofarads of bootstrap capacitance. One more detail is dead time control. So as we did for the last driver stage, we also want to do dead time control for the power stage itself. So why is that? Because we don't want to damage the power stage by getting these cross currents. So, and if we leave the dead time too long, we get losses. Losses are related to the forward conduction and reverse recovery of the body diode. So there are various concepts which I would briefly like to summarize. So the easiest is to make use of delays of CMOS inverters. That's very simple, but it needs some design margin as you want to be safe over corners. The other one is similar to the break before make circuit, which we have seen before already. So probably go quickly over that. The most effective but also most complex is a predictive dead time control. This is actually what my group has implemented a couple of years ago, and there's various more examples. What we do is we look at the switching node voltage if we turn on the low side device, and we want to make sure that we switch if the switching node is around 0 volts. And if this, and to relax the speed requirements, we store this voltage on a capacitor in a sample and hold stage, and then go into a window comparator and increase and decrease a counter. So with that, we can reduce the losses by roughly 30% and even increase the efficiency then by 6% in this example. And the whole thing runs even at 10 megahertz. So that brings me to the topic of level shifters. Level shifters we have looked at already. So we know the resistor-based level shifter, the cross-coupled level shifter, with some pros and cons. And especially for higher voltages, this cross-coupled level shifter sees the full source gate voltage here of these PMOS devices equal to the gate drive voltage. So that's of course to the supply of the high side, and that's why we need to have a high voltage version of that cross-coupled level shifter, which is shown here on the right. We insert simply high voltage cascode transistors, which could be biased from the switching node. So now the P devices can be low voltage devices, and the other ones still high voltage, and everything is protected. We also notice that the source gate voltage here blocks the gate driver input level from going to 0. If we don't want to have that, we can add additional switches like M7, M8, and even more, we can also add 2 more CMOS inverters to basically increase some loop gain and get the full swing driving of the gate input. That's all nicely summarized in this paper here, Isscc2020 T2. This slide here is something, if you are proceeded in these talks, everyone gets a little bit tired. I intended this slide just to give it to you in case you need to get back to it later on. In the end, we need to make sure that our N-type device is strong enough to fight against the PMOS. This is not so common, but in this case, our PMOS sees the full drive voltage at source gate, so it's turned on quite heavily, and the NMOS needs to fight against it. If you do all these current equations, then we find the sizing equation here. And likewise, for the cascoded high voltage version, there's one more device. That's why you get one more equation. So in case you want to make sure everything works, you can refer and get back to these equations. Control loop. So let's again put now everything together. We have the power stage, our LC filter, and then we hook the output voltage by resistive divider to the error amplifier, which sees the reference voltage here at the positive input to give the reference level for the out. So how does the whole thing work? So we have a switching behavior, and at the beginning of each phase, we turn a sawtooth generator on, which ramps up this Vs ramp voltage. And as soon as the crossover between Vc and Vs happens, we set our PWM signal to 0. That means our high side transistor turns off. And as soon as we turn off, so during the first cycle it's turned on, we bring energy into the system, and as soon as we turn off, this diode here, in this case, very simple example, it acts as a freewheeling diode to carry the current of the inductor. And now let's assume we pull down the output voltage. So our error amplifier, so the load increases, our output voltage goes down, the error amplifier has an inverting behavior, and Vc will then go up. And in the end, our turn off point, the crossover point, happens at a later time. And so we simply have a longer period in that we turn on the high side device, so we bring more energy into the system to counteract the increase of load at the output. So this is how the regulation works. Of course, we have some LC time constant, which makes it slow, but in the end it works. So this is the most common principle known as voltage mode control for, or the most easy concept for DC-DC conversion. Now let's look at some circuit blocks. The error amplifier is actually quite simple. We don't want to have too much gain to ensure loop stability, and so we find symmetrical op-amps as well as cascode structures to be used as the error amplifier. In particular, the GM of these stages is critical because it is part of the transfer function. So in this simple case, it's basically the GM, the transconductance of the input differential pair. One interesting aspect, if we start up our regulator, our output capacitor is fully discharged, and we would get a large inrush current. So this little picture here indicates what we would see. Our output voltage would immediately jump up with the maximum speed, and we get even some ringing and a lot of stress. So we don't want to have that. Usually we have a requirement of ramp voltages in the range of 1 to 10 volts per millisecond. And in order to ensure that, we can take our error amplifier and basically add a soft start circuit, little circuit here, which bypasses one of the differential transistors at the input, in particular the one that is hooked up to the reference. And now, as soon as we enable our DC-DC converter, this switch turns off, and this current source charges this capacitor to with the same ramp of a few volts per millisecond. So, and if you do calculations here, we find if we allow ourselves a small capacitor here, we find a current which is very small. 10 nanoamps needs to be provided here to this 5 picofarad capacitor. And how can we generate it? We use a current mirror, but this violates all the rules that we have learned about matching. So it's a very odd current mirror, 10/1 and 1/10, but it works. There's quite a large spread, but usually the specifications allow quite of a range of this startup, as long as our ramp is in the range of 1 to 10 millivolts per millisecond. So one little detail on soft start. The next is on the sawtooth generator. The most simple concept is we charge a capacitor with the current source. This is the simple idea, but to be compliant with the common mode range of the comparator, we want to start with a little bit higher value, and so it's convenient to use this kind of active integrator circuit. Of course, there is some finite settling time if we reset the ramp generator all the time at the beginning of the phase. So in particular for fast switching converters, we eat up some of our duty cycle resolution. And one way to address it is to go into a time interleaved approach by using 2 of these ramp generators. So let's look into the loop again. So I'm watching the time a little bit, so probably we skip a few steps here. Equations are always scary. So what I would highlight now with these colors here, basically we have the plant, which is this yellow box here underneath everything, and we have the controller, which is this greenish box here. And if you calculate the loop transfer function, we have roughly 1/alpha, which is the feedback resistor ratio. This is the blue box here. So that's exactly what we want to have. Now if we want to keep the loop stable, we need to look at the loop gain here in the denominator, which is G times H, so the yellow times the greenish block. Let's first look into the modulator transfer function, which is consists of 2 parts, the pulse width modulator and the power stage. Also one comment here on the colors. I think in the printout the colors were flipped, so we need to correct that. So it maps to the final transfer function that we get here. So the bottom line is we have 2 DC values, Vin and Vs max. Vs max is the maximum ramp voltage that our ramp generator reaches at the end of the switching phase. And then we have a double pole which accounts for the LC components here. So, and we need to compensate that by inserting poles and zeros in the controller, and that's the sizing of this little box, this box here with the at the end of at the output of the error amplifier. And I would also like to show one example. So there are various types to implement these compensations. They are classified in type 1, 2, 3, and variations of that. So this is very common here, this type 2, which inserts 2 poles and zeros by using capacitors here, C1, C2, and R1. And in the end, if we do the calculations, we have some integrating behavior with the pole at 0, and then a 0 and a pole. And now let's assume we have a required VZ, FZ, and FP frequency. Do the calculations, then we come to quite large capacitor values. In this example, for roughly 4 nanofarads. Now the question is, how do we implement it? You can place them externally, but more and more products nowadays require to have those components inside the IC, so that users do not need to bother with all these equations and transfer function and stability and so on. So, and we can make use of what we know, we have talked about it already, the Miller effect. This is one example which helps to increase the value of a capacitor virtually by a gain factor of alpha, of A, not alpha. In this case, it's A. And this would be the voltage mode operation. And for DC-DC converters, current mode is actually much more convenient. It uses a current-controlled current source, which senses a current in a capacitor, relatively small capacitor value, and provides K times that current. And in the end, that virtually acts as a capacitance value increased by that K factor. And one of the example implementations was published by our colleague Kehon Chen from Taiwan, where they use two resistors actually by means of transistors here. They are fully switched on, so they are resistors. They are scaled by a factor of K, and a power amplifier voltage follower equalizes the source voltage so that we have K times the current flowing here. And that allows us in this, in our example, to get away with 200 picofarads that behave as a 20 times larger capacitance. So, and there are much more nice benefits if you keep these switches here. You can even configure your controller behavior during the operation to make it more stable or unstable and react to transients and so on. So there's, so far we looked into voltage mode control, and there's more control mechanisms. One is the so-called current mode control, which now replaces the sawtooth generator by a ramp that we see in the inductor current. So the current will be a ripple current going up and down, and if we sense that and bring it into the voltage domain, we can also fulfill a control. It looks a little bit more complex indeed. On design side it's more complex, but the overall behavior is more simplified. We achieve a one-pole behavior, and so we really, there is a need to more and more implement current mode control in DC-DC converters. So I'm watching the time a little bit. So what I suggest is we keep in mind we have a current sensing stage here, which we talk about still. The overall transient behavior I would skip for now. Bottom line is that this additional loop simplifies significantly to be just 1 over R sense. It's a DC value. There is no AC behavior to it, and that's why the whole overall loop, even though it looks more complex, is a one-pole system shown here. And we can, or the modulator transfer function is a one-pole system, which is much easier to be stabilized. In the end, there's no free lunch. We still have some interesting challenges here for current mode control, and that's related to some perturbation we may get depending on our conversion ratio on the duty cycle. So there may be some disturbances that actually go up and down and have a frequency which is half the switching frequency, and that's why it's called subharmonic oscillations, which can be addressed by subtracting a ramp from the compensating from the compensator output voltage we see. So and that ramp again needs to be generated. It adds more complexity to this circuit diagram. There are two options. So either we subtract or we add a slope to the ramp signal that we sense from the inductor. So these options, there are also some interesting design implementation examples. I suggest that we just briefly look at it and basically skip it for now. So the bottom line here is that we do that in the current domain. So if you want to subtract or add some values, you convert them from voltage to current, and then we can fulfill the slope comparison here. We feed it into the power stage and so on. So we do that in the current domain. This is option 1, and there's option 2 as well. I've taken a picture here from one of the early papers from Philip Mark's group in Hong Kong on current sensing. Again, these little blocks here out of their paper is a V2I conversion, and then we add a ramp to the sense current signal. So let's talk a little bit about current sensing, if we need it here. So there are various ways for this kind of current mode control, but this is also for protective purposes to keep a safe operating area of the power transistor. For instance, here it shows the drain current and the drain source voltage. So there's various reasons to do current sensing. The most simple current sensing would be simply to use our power transistor and to detect the voltage drop across it. It's a measure of the current, but it gives us only relative accuracy. A very widely used concept is so-called replica sensing. Here we use our power transistor, and we have learned that there are multiple fingers usually for the power transistors. We use one finger to sense that current. So we have a ratio of 1 to M, and M can be in the range of 1,000 to even 10,000. So, and we have a control loop that maintains the voltage on both sides almost equal, or equal, ideally equal. And this way we get an output current which is a 1 over M scaled version of the input current. So I'm using these colors to put together a block diagram, and we can do calculations, and that indicates that we have this kind of transfer function which should be 1 over M, so that confirms everything. However, it also confirms that these kind of circuits are relatively slow. So in other words, the gain bandwidth of that amplifier gets scaled down by a factor which is smaller than 1, as this sense resistor is in a range of 1 kilo ohm, and the output resistor is like 100 kilo ohms. So that's why these circuits are relatively slow. So there's a lot of literature that talks about that it's slow, but nobody really calculates it. That's why I added it here just to indicate it. So there's more practical aspects. How do we implement this amplifier here with common gate configurations? And due to the biasing here, there is some more aspects to compensate these bias currents. So I really don't want to stress the time too much. I promised you to be done in time. That's why I recommend to go across that quickly and talk a little bit in the remaining few minutes about system level design aspects. And these include, of course, protection diagnostics. We have some power dissipation. So we really want to make sure to protect our IC against over temperature, also against over voltage and over current. And then there are these three cases which all come together: short to ground, short to battery, and open load, so really failure cases. And we want to make sure that we don't drive our power transistor with insufficient gate voltage, so under voltage lockout is also required here on top level. Thermal protection, we usually always have a temperature sensor on the chip. We can use that to flag a thermal shutdown, and we allow the whole system to cool down. We stop our PWM until the whole system cooled down. Floor planning, as we now have analog, digital, and high voltage, we don't want to intermix them. That's the bottom line here, as the high voltage protection is usually fulfilled by spacing, and we don't want to scatter our floor plan around. So most of the other things I mentioned already. We benefit from thick copper to get all the current across the die. Thermal analysis to make sure we don't have too many hotspots on the die. And the grounding supply rules are similar to what we know for other designs as well. We don't want to mix these different groups here. We want to have a star connection to keep noisy lines, supply lines, and sensitive analog lines separated. Indicated also here in this example, if the current is very high, we want to even use 3 connections, either bond or flip chip connections, to get sufficient current through. So that brings me to the end of the talk. We've seen that we have a variety of energy sources from very low millivolts up to 48 and even 100 volts. And we want to provide the proper power level and voltages to our functional blocks. At IC level, looked at various blocks. So it's a lot of challenges, but it's a lot of fun as well. I also would like to highlight some of the talks that we see at this year's Isscc. We actually got 3 sessions on DC-DC and power management. In session 11 on Tuesday, we have a resonant SC converter, so it's a switch cap converter, but it has L and C fully integrated on chip with some interesting level shift and switch stacking design. There's one more high voltage DC-DC converter. It's actually for my group, which has an interesting bootstrap supply. Then we have one design which uses gallium nitride for power conversion. Then one more design with adaptive dead time control. So we talked about that. Session 18 on Tuesday in the afternoon is GaN and isolated power. There's one design which is not in silicon, which is purely in gallium nitride. And that's actually also a design of my group, which addresses a 400 volts offline converter, including the control loop. Then we have a high power converter with a dynamic level shifter. And finally, there's session 32 on Wednesday, which has, among others, interesting piezoelectric energy harvesting. There are some references, and that concludes my talk.